Hello everyone, in this video we'll continue where we left off and build a full layer for a feed-forward neural network. First, we'll do a quick recap of the neuron module from the last video, then we'll modify the design so that the same Verilog code can be used to process an entire layer. Finally, I'll show the pulse generator timing needed to drive the layer calculator circuit. As a reminder, the end goal of this series is to build a simple feed-forward neural network with 3 layers and 60 neurons. We're going to write the Verilog code for the entire network, and then we're going to deploy it on an FPGA and do real-time image classification. Images will be sent from a computer to the FPGA over UART. The FPGA will run inference on the network and output the classification result in real time. And this is a pretty serious build. This project alone was enough to count as a master's thesis, so we're going to take it step by step. Before we continue, I want to quickly mention the mission behind this channel. The long-term goal is to turn TrueSight Labs into a non-profit organization focused on digital design and hardware engineering, so that motivated people can go from knowing nothing to being an expert in the shortest time possible. If you want to build your skills while simultaneously pushing that mission forward, you can support the mission by purchasing the book. The description includes an Amazon link for the physical copy and a Stripe link for the digital copy. The book is priced similarly to what a typical high-end university textbook would cost, and purchasing it grants you full access to all future course updates. The end goal of this video series is to deploy a standard feed-forward neural network on an FPGA, like in the diagram shown below. In the last video, we wrote Verilog code for a single neuron on an FPGA. In this video, I'll show how that same design can be scaled up and reused to calculate an entire layer. To recap the last video, a neuron takes an input vector x, a weight vector w, and a bias b. It computes the dot product w.x and then adds the bias b to produce the neuron's output. In the last video, we defined a simple memory layout so we can store a neuron's inputs in a predictable, controlled way. Then, we designed a complete circuit that implements the mathematical behavior of a single neuron. In this video, I'll show you how the exact same architecture can be reused to implement the behavior of an entire layer. If you have not watched the previous video, then it's extremely important that you go watch it first, since this video will build on what was already done. So in this video, we're going to design a circuit that implements the mathematical behavior of an entire layer. A layer is simply a group of neurons. Every neuron in the layer uses the same input vector x, but each neuron has its own weight vector w and bias b. Each neuron produces one output value, and all of those outputs together form an output vector. That output vector becomes the input vector to the next layer. The great thing about the neuron calculator circuit from the last video is that its hardware can be used to calculate an entire layer with no modifications. Only the storage changes. The ROMs go from holding one weights vector and one bias to holding the weights vectors and biases for all the neurons in the layer. In a layer, we need to store multiple biases and multiple weights vectors. We can do that with the memory layout shown below. The bias ROM is simple. Store B0, B1, Bn at addresses 0 through n, where n is the index of the last neuron in the layer. The weights ROM stores the vectors back-to-back in contiguous blocks. Each neuron's weight vector Wn occupies its own block of addresses placed right after the previous one. The input vector x is stored at the exact same way as in the previous video, so there's no change needed there. Just to make sure that you understand the memory formatting, let's do an example. If the first layer has 30 neurons and the input vector is a flattened MNIST image, how should the XRAM be formatted? Go ahead and pause the video and come back once you've tried it yourself. A flattened MNIST image has 784 elements, so XRAM stores X0 through X783. That means it uses addresses 0 through 783. Now in this same situation, how should the WROM be formatted? Go ahead and try it yourself first. Since the input vector has 784 elements, each weight vector W0 through W29 also has 784 elements. If we store the weight vectors in contiguous blocks back to back, the ROM is to be partitioned like this. Now in the same situation, how should the BROM be formatted? Go ahead and try it yourself first. Since the layer has 30 neurons, we need 30 bias values, B0 through B29. The bias ROM is indexed by a neuron number, so we store them like this. This is the final layer calculator circuit. Once all 3 memory blocks are initialized, we can drive the module with the input pulses to compute every neuron in the layer, one after another. Notice that the architecture itself hasn't changed from the single neuron design. The data path itself is the same. The only differences are 1, that we store more data in memory, many W vectors and many biases, and 2, the address generators count differently, so we step through each neuron's block of weights and its corresponding bias. So how do the address generators change? The good news is that they actually stay very simple. Each address generator is still just a counter. The only thing that changes is the range that each counter needs to cover, and the rules below describe all 3. And the reason we can keep the address generators this simple is because of how we formatted the data in memory. In an AI accelerator, one of the biggest challenges is choosing a memory layout that makes data retrieval easy. If the data is stored cleanly, the control logic becomes clean too. So now that we've covered how the circuit works, the only question left is, how do we drive it? Well, this is done by systematically pulsing the inputs in a controlled way. To explain how the pulse generation works, let's walk through a concrete example. Before we start, one important note. In the last video, I show an animation that makes it very clear how the data moves through with each pulse. If you have not watched that video yet, go watch it first, because this explanation builds directly on it. Now the diagram below shows how to process the first neuron in a layer when the input vector has 784 elements. First, apply the reset pulse to clear the accumulator and return the address generators to their initial states. Next, apply a repeating burst of P1, P2, and P3 pulses. Each burst computes one term of the dot product. P1 increments the W and X addresses. P2 reads out WI and XI from memory. P3 multiplies them and accumulates the results. So after the first burst, the first term has been added. After the second burst, the second term has been added. This continues until time t784, when all 784 multiply accumulates are complete and the dot product is finished. After the dot product is done, apply P4 and P5 to read and add the bias. Then apply P6 to write the final neuron output to memory and assert neuron done to mark that the neuron computation is complete and to prepare for the next neuron. That's the full pulse sequence for computing the first neuron in this example. So how do we process the next neurons in the same example? To calculate the next neurons in the same layer, we simply repeat the process we used for the first neuron. The timing diagram shows this clearly. The green region calculates the first neuron, the pink region calculates the second neuron, and the blue region calculates the third neuron. By continuing this pattern for all neurons without pulsing the reset again, we can evaluate the entire layer for an input vector that is 784 elements long. So in summary, a layer in a feed-forward neural network can be implemented using 2 modules. The main module is the layer calculator. That's the module that we just studied. The second module is the pulse generator. Its job is simply to generate the control pulses that drive the layer calculator. I'm not going to build it in this video because it's straightforward in principle and would mostly be a control/state machine exercise. Later, I plan to make a short waveform generation series that shows how to design modules like that from scratch. If you bought the book, you'll have access to a parameterized pulse generator module that lets you deploy any layer immediately. You simply set 3 parameters and the same module can drive any layer configuration. In the next video, we'll finalize the full AI accelerator. I'll show the UART streaming circuitry, how the full feed-forward neural network is assembled, and how the 7-segment controller is connected. That's all for now, and see you next time.